All right, let's continue our discussion of the first derivative test. So we have three more examples here where we want to identify all local extrema. And then, of course, that means we need in order to apply the first derivative test, we need to find the increasing and decreasing behavior of the functions. That means we need to fill out our sign chart for the first derivative. So let's hop right in with example one. Here's our first trig example. Now notice we do have a restricted domain for that trig for our trig example. Why? Because when you're dealing with periodic functions like sine and cosine or otherwise, a lot of times you get an infinite number of local extrema if you consider the entire domain of the function. So here I want to only specify solutions, local extrema, um, in the basically in the 0 to 2 pi in 0 to 2 pi, the closed interval. So that'll give us a finite number of solutions instead of an infinite number of solutions. What's our first steps? Of course, we need to find the derivative. Okay, so f prime of x. Oh, this is pretty easy. What's the derivative of 1/2 x? Well, it's 1/2. So of course, we're applying the sum difference rule for derivatives. So we take the derivative of 1/2 x and cosine x individually, the derivative of 1/2 x being 1/2, and the derivative of cosine being negative sine. So our derivative was easy enough. Okay, and now we need to solve, of course, to find critical values. F prime of x equals 0. So that's what? 1/2 minus sine x equals 0. Oh, in other words, that means sine x equals 1/2. Okay, so this is actually a pretty straightforward, a calculation that we just need to basically have our unit circle memorized for. We're only looking for solutions on 0 to 2 pi, so one revolution or one rotation, or mixing up the words now, of our unit circle. Um, so let's see, sine's 1/2, so that's positive 1/2. Where is sine positive? Sine's positive in the what? First and second quadrants, because you're talking about y values. So where are the y values positive? So we only really have to worry about the top half of our unit circle, which is good because I can't draw a circle, so that's a terrible semicircle, but hey, I guess it gets the job done. Now where's the sine 1/2? Where's the y value 1/2? Well, I think it's 1/2 over here, and the coordinates of that point are what? Root 3 over 2 comma 1/2. And then what about the reflection over here, where those coordinates are negative root 3 over 2 comma 1/2. Okay, so what are those angles? Well, the first angle is what? Pi over 6. The second angle is pi minus pi over 6. Okay, because the straight angle is pi, right? And then minus pi over 6. So what's pi minus pi over 6? This is how I like to think about unit circle. Yeah, I don't necessarily. I mean, I use it all the time. So I know the unit circle, but to me, I like to teach the unit circle by memorize the first quadrant and then just use your mathematical intuition to find the other angles. So if we know the straight angle is pi, and that little angle is minus pi over 6, to back up pi over 6 radians, well, okay, well, you just get a common denominator. 6 pi over 6, so it's 6 pi over 6 minus pi over 6, of course, gives you 5 pi over 6. Okay, so there's our two critical values. Okay, now, are there any values where the function's not differentiable? Well, look at the derivative. Okay, here is our derivative. Let me box it off like we usually do. There's our derivative, but our derivative is a constant function and a trig function. Both have domain all real numbers, so no, this is a nice, smooth, continuous curve. No cusps, no funny business with vertical tangent lines or cusps or anything. Okay, so we only have two critical values, and they are pi over 6 and 5 pi over 6. And so there are our critical values. Okay, so now we can get to the business of our sign chart. Now, remember, our domain is restricted. We're only considering 0 to 2 pi. So, instead of having a number line from 0 to infinity, we have a number line with 0 to 2 pi, and we have, pi over 6 here, and we have 5 pi over 6 there. Okay, so that's another mistake I see where students will miss a test question or a homework question because again they're just always in that autopilot mode of thinking, okay, the domain's all real numbers, so let's have a negative and positive infinity on both sides of our on both the ends of our intervals. But here we have a restricted domain from 0 to 2 pi. So we go ahead and get our chart going, our sign chart. First row, of course, is your intervals. And we have 0 to pi over 6. And again, we're always using open intervals. 0 to pi over 6. And then we have pi over 6 to 5 pi over 6. And then we have 5 pi over 6 to pi. Okay. Now we need to pick test points. Now, sometimes it can be a little weird to get your test points here because we want test points that are convenient. If pi over 6 is right here, there's not really a nice unit circle, radian measure that we can use. I mean, I guess we could say pi over 12, but again, that's not, we could use pi over 12 and maybe use the half angle identity, I suppose. But that's, I mean, sure, we could do that, I guess. It wouldn't be cool. But to me, I mean, basically, what's pi over 6? Pi over 6 is approximately 0.52. So what's a number between 0 and 0.52? You can just say 0.5 and then use a calculator to figure out the sign. Okay. Pi over 6 to 5 pi over 6. Well, what's a nice convenient angle on the unit circle in between? Well, pi over 2 is a nice convenient one. What about 5 pi over 6? Again, what's a convenient one? Well, there's pi's in there. That's a nice one that's between 5 pi over 6 and 2 pi, or 3 pi over 2. But I'll put a pi there because that's a quadrantal angle. I mean, there's plenty of choices there, but pi is probably as good as any of them, or better than most. But pi or 3 pi over 2 would probably be the best there. Okay, so now we go to the sine of f prime. So the sine of f prime okay. Here's actually a way you could think about this first one, without even really using your calculator. Of course, you could go to your derivative, plug in a 0.5, and see what the answer is. But just looking at your unit circle, the y value here on this point right here is 1/2. If your radian measurement is smaller, that means the point is going to be lower, which means the y value of the sine of that angle is going to be less than 1/2. So if you have 1/2 minus a number less than 1/2, is that overall going to be a positive or negative answer? Well, if you have 1/2 minus a number less than 1/2, that should give us a positive answer. Now you can verify using your calculator. Let's see, what's 1/2 minus sine of 1/2? It's 0.02, positive, like I said. Okay. What about pi over 2? Pi over 2 is what? Sine of pi over 2, that is. So I'm plugging in to my derivative, just mentally. So 1/2 sine of pi over 2 is 1. So you have 1/2 minus 1, negative 1/2. So negative. What's pi? What's specifically sine of pi? Sine of pi is 0. So 1/2 minus 0 is 1/2, positive. So what are the results? Where the derivative is positive, increasing. So we're increasing over those intervals where the derivative is negative, decreasing. So we're decreasing in the middle. Okay, so what does the first derivative test tell us? The first derivative test says if you change from increasing to decreasing at a critical value, which pi over 6 is a critical value, then you have located a what? A local max. So we have a local max at pi over 6, comma, something. All right, we might have a local min too, so let's go ahead and put that down. Notice also that we have a change at 5 pi over 6, and that changes from decreasing to increasing at 5 pi over 6. Again, the first derivative test tells us that if you change at a critical value from decreasing to increasing, then you found a relative minimum. So 5 pi over 6 is going to be a relative minimum, a local minimum. Now, I suppose we should find the y values. The y values mean we need to go to the original function. So this is going to take a little bit of scratch work probably. So that means if you go to the original function f, so f of pi over 6 means 1/2 times pi over 6 plus cosine of pi over 6. This is going to be a not fun y value. That equals what? Okay, pi over 6, that's what, pi over 12? Pi over 6 times pi times 1/2. And then what's cosine of pi over 6? Cosine of pi over 6 is √3 over 2. Okay. So this happens with a lot of times with trig functions. What's the common denominator going to be? It's going to be 12. So multiply by 6 over 6, and we get what? Pi plus 6 square roots of 3 over 12. That's a nice looking y value. It's good to do exercises like this so you don't always just get nice integer answers. Pi plus 6 square roots of 3 over 12. And now let's do the same thing for 5 pi over 6. What's f of 5 pi over 6? Well, that's going to be 1/2 times 5 pi over 6 plus cosine of 5 pi over 6. All right, so that's what, 5 pi over 12 this time. And what's cosine of 5 pi over 6? Okay, 5 pi over 6 is this situation over here, which has a cosine value of negative √3 over 2. So we get common denominator, multiply by 6 over 6 again, and we get 5 pi minus 6 square roots of 3 over 12. Nice looking y values. So 5 pi minus 6 square roots of 3 over 12. All right, fun times there. We'll check it to make sure those are good. I'm gonna jot down the increasing, decreasing behavior as well. So we have our local extrema, of course, and then we have what? The f is decreasing on what? It was decreasing on 5 pi over 6. Nope, sorry, that's pi over 6 first. Pi over 6 to 5 pi over 6. And I just wrote a 5 again. Pi over 6 to 5 pi over 6. And f is increasing on, we said what, 0 to pi over 6 union 5 pi over 6 to 2 pi. And there we go. I think we've done all of the first derivative analysis we can do on that function. Okay, so let's get this little bit of scratch work out of the way, and then we'll take a look at example B. All right, so B, we have a radical function, or the difference of two radicals. Okay, So let's see. Radical functions end up a lot of times being interesting graphs. A lot of times they have cusps or vertical tangent lines. Weird stuff like that, like we've seen in the past. Of course, our first step is to find g prime. So g prime, okay, is a constant multiple rule, 1/2. Now we apply the power rule, 2/3 times x to the negative 1/3. Minus, now just apply the power rule, 1/3 x, okay, 1/3 minus 1 is negative 2/3. Now, of course, we need to clean this up a good bit. So this gives us what? The twos divide out. So that gives us 1 over 3x to the 1/3 power minus 1 over 3x to the 2/3 power. Okay, interesting. So we have a denominator of a 1/3 and a denominator of x to the 1/3 and x to the 2/3. What would our common denominator be here? I think it's going to be an x. Okay, that is, if I multiply this fraction by x to the 1/3 over itself, and I multiply here, let me move that equal sign just slightly. If I multiply the left-hand fraction by x to the 2/3 over itself, I think what I'll end up getting is, let's see, that's going to be x to the 2/3 on the numerator here, and then minus x to the 1/3 on the numerator there. But on the bottom, I'll have what? I'll have 3x, because x to the 2/3 times x to the 1/3, you add the exponents, you get x to the 3/3, which is x to the first power. So the denominator ends up being a nice 3x. Here, let me fix that terrible 2. It's 2 over 3. 2 over 3. There we go. Okay. So we have x to the 2/3 minus x to the 1/3. Do note here, I'll go ahead and talk about this while we're here. So there's g prime. I'm going to box this off. Right away, I notice what about g prime? G prime is not defined at 0. That is, the function's not differentiable at 0. But 0 is in the domain of the original function. So that means that 0, something funny is going on there. In fact, it's a critical value. X equals 0 is a critical value because g prime of 0 does not exist, but g of 0, the original function evaluating 0, does exist. So that means either graphically there's going to be a vertical tangent line or a cusp. One of those two things is going to happen. Okay? Because the function is continuous at g. Sorry, the original function is continuous at 0, but the derivative is not continuous at 0. So 0 is a critical value. There's one. But now, of course, we need to do our usual solving g prime equals 0. So g prime of x equals 0. That's x to the 2/3 minus x to the 1/3 over 3x equals 0. Now, again, you've heard me say this so many times now, that is a quotient. And a quotient set equal to 0, all you have to worry about is the numerator. So we can instead focus on x to the 2/3 minus x to the 1/3 equals 0. Okay, how do we solve this? We need to factor it. What can we factor out? We can factor out x to the 1/3. Greatest common factor here would be x to the 1/3. Now, it's kind of weird to think about this sometimes. Clearly if I factor out an x to the 1/3, a negative 1 goes there. But sometimes it's kind of tricky to think about what goes where the 2/3 was originally. You kind of like undo the distributive property in your head. Well, how do you, if we were going to redistribute what would need to go here? What would need to go right here, question mark, such that when you multiply it out, you got x to the 2/3. Well, whenever you multiply power functions with the same base, you add the exponent. So I think x to the 1/3 would go there. Because if I distributed, I would have x to the 1/3 times x to the 1/3, which you would add 1/3 plus 1/3, you get 2/3. So yeah, that's the correct factorization. And now we can use the zero factor theorem. To set each factor individually equal to 0, we could say either x to the 1/3 equals 0, which implies that x equals 0. Or we could say x to the 1/3 minus 1 equals 0, which implies that x to the 1/3 equals 1. And if you cube both sides, you get x equals 1. Okay, now notice we already had 0 as a critical value, so that's just extra information now. Who cares? We already had it. But there's a new critical value. Again, we already had 0 as a critical value. So again, just to highlight, we have 0 and we have 1, and we now need to divide our number line. Now, what is the domain of the original function? Okay, we've said this a few times now. We have a cube root, which has domain all real numbers, and we have a 2/3 power, which again has domain all real numbers. So the domain of this function is indeed all real numbers. So we're going to divide up the real number line from -infinity to +infinity. And our critical values were 0 and 1. So we're going to have 3 intervals to consider when we make our chart. Okay, so let's see here. Sign chart. Oh, let's see here. We got plenty of space down here. Let's do something. So let's make a sign chart over here. So we have the first row is going to be your intervals. Intervals. Well, we have what? We had -infinity to 0. And then we have 0 to 1. And then we have 1 to infinity. Next up, test points. So we have, I'll pick a -1. Okay, we have 0 to 1. There's not a good integer there, so we'll have to pick 1/2 will work. And then let's pick 2. And then we're going to say sine of g prime, the derivative. Now let's see. Okay, let's see. Okay, I'm going to have to scroll back and forth here. My first test value is a 1. So if I plug in a 1, clearly the denominator is -3. So let's go ahead. I'll jot this down so we don't lose track. -3. Now on the top, it's going to be -1 squared is +1. Cube root is 1. Okay, minus. Okay, the cube root of -1 is -1. So we get 1 minus 1 is 2 over -3. It's a negative value. Okay, so there's our first result. First sign is negative. Okay, now we need to plug in a 1/2. Okay, remember we're only concerned about the signs here. So if we plug in a 1/2 on the bottom, 3 divided by 2, multiplied by 1/2 is 1.5. It's positive. Now, what's 1/2 to the 2/3 power? I don't really care much. 1/2 squared would be what? 1 over 4. It would be 1 over the cube root of 4. I don't even know what that is approximately. 1 over the cube root of 4. Let's just say 0.5 raised to the 2/3 power. It's about 0.62. Let's just say 0.63. If it gets close, we'll have to get more decimals. But let's just say it's approximately 0.63. Minus, okay, we're plugging in a 1/2. And what's the third root of 1/2? So 0.5 raised to the 1 divided by 3. Okay, it's about 0.79. So 0.63 minus 0.79, that's negative, over 1.5 is positive, so overall it's negative. Okay, so notice I told you this would happen. Two negatives in a row. You know, a lot of times we get, you know, the alternating plus, minus, but here we have the two negatives. Okay, and now look at our last test point was 2. So let's see what happens when we plug in a 2. On the denominator, obviously 2 times 3 is 6. So the denominator is positive. But on the top, you would have what? The cube root, you know, 2 to the 2/3 power would be 4, the cube root of 4. So 4 raised to the 1/3 power. It's about 1.59 approximately. Minus, okay, we're plugging in a 2. What's the cube root of 2? Well, it's 1.25 approximately. Okay, so 1.59 approximately minus 1.25 approximately. It's a positive numerator over positive denominator, so the overall result is positive. Okay, so here is our complete sign chart. Now we can, you know, fill in our results. We are decreasing where the derivative is negative and increasing where it's positive. And now we can apply the first derivative test. Okay, so the first derivative test says if you change from either decreasing to decreasing at a critical value or increasing to increasing at a critical value, then you have not found a local extrema. So notice at 0, we're changing from decreasing to decreasing. So we haven't found an extrema because there is no change from decreasing to increasing or vice versa. It was just the sign was negative on both sides. So we haven't found an extrema. Okay, but notice at x equals 1, we have a change from decreasing to increasing. So we could say there's a what? There's a local minimum at 1 comma something. And since there are no other critical values, there's no more possibilities for any other local extrema. So as far as a local max is concerned, there are none. Okay. If we want to jot down the behavior, we could say, you know, the increasing, decreasing behavior, we could say G is increasing on, well, it was 1 to infinity. That's a terrible infinity sign. 1 to infinity. And G is decreasing on, what was it, negative infinity to 0, union 0 to 1. Now let's to find the y value of the local minimum, we need to go back to the original function and evaluate at 1. Okay, so original function, if you plug in a 1, you get 1/2 times 1 to the 2/3 power, which is 1, minus 1 to the 1/3 power, which is 1. So you get 1/2 minus 1 is negative 1/2. So negative 1/2 it is. Okay. Oh, let's do one more, I guess, then we'll check these all on Desmos at the end. So I forgot to do the first one. So last one, and then we'll look at Desmos. All right, so with part C, we have some logarithms. It's been a little while since we've had logarithms. Always fun. So let's look at the derivative. We got to find the critical value, so let's just find the derivative first. So h prime, all right, notice it's composite. It's kind of a weird composite function, but it is composite. Let's see, so the outside is just natural log x, the inside is 1 minus natural log x. So, you know, a weird composite function here. So we take the derivative of the outside function, which is 1 over x. We then evaluate at the inside function. So we, instead of x there, we write the inside function, 1 minus natural log x. we then multiply by the derivative of the inside function. Okay, well, the derivative of the inside function, the derivative of 1 is 0. The derivative of natural log x is negative 1 over x. So if we multiply this out, we get h prime equals negative over x, 1 minus natural log x. Just multiply numerators, multiply denominators. So there's your derivative. Okay. Let's set it equal to 0 and solve. So solve, like always, derivative, set equal to 0. So we have negative 1 over x, 1 minus natural log x equals 0. You've heard me say this like the 10th time lately. We have a quotient set equal to 0. All you have to worry about is the numerator set equal to 0. So we get negative 1 equals 0. Okay, that's weird. I'm not sure we've seen that before this semester. Negative 1 equals 0. That's what you call a contradiction. There's no solutions. So the derivative can't be 0. Interesting. So what does that tell you? Well, my first reaction is no critical values. If there are no solutions to h prime equals 0, then maybe there's no critical values. But then I have to back up and say, okay, but it's possible we have other critical values that are the result of differentiability issues. So we need to look at the domain of the derivative. So you might say to yourself, okay, obviously, okay, if I box off the derivative here, obviously there's a 0 here on the bottom, and the original function didn't have a quotient, so maybe 0 is a problem. But, okay, so 0 is clearly not in the domain of the derivative. But remember, the logarithm, the domain of natural log x, is positive numbers. You can't plug 0 into a logarithm either. So, okay, so 0 almost looked like it was going to be a critical value, but it's not, because 0 is not in the domain of the derivative, nor is it in the domain of the original function, okay? And then also notice that, well, what the heck is the domain of the original function? Okay, so to find the derivative, sorry, to find the domain of a logarithm, what you do is you set the argument is this part, you set the argument greater than 0 and solve. Okay, well, how do you solve that? So this is just a college algebra review, by the way. How do you solve 1 minus natural log x greater than 0? Well, basically you would solve the corresponding equation. So you would say, all right, well, let's consider 1 minus natural log equals 0 instead. So 1 minus natural log x equals 0. Of course, that means that natural log x equals 1. And using the definition of a logarithm, that means e to the 1 equals x. So e is the we call the boundary point. It's the solution to that equation. Now, what I'm doing here is I'm actually doing the exact same process we do with the derivative, except I'm doing it with the original function. So no derivative here yet. So I'm making that sign chart with the original function, just like I did a couple videos again when I did that little college algebra review. So what I've done here is found what I called the boundary point, or the boundary value. So that means at x equal e, so the domain of a logarithm, the lowest is this well, there is no lowest value. It can't be 0, so it's open interval from 0 to e, and then from e to infinity. Okay, so at those are my intervals. Now I need to figure out where is it positive, where is it negative, because I need that to be positive, because it's in the argument of a logarithm. So intervals, I'm going to do test values. Well, what's a number between 0 and e? E is about 2.7. Okay, so 1 is there. What's a number bigger than e? 3. And then we're going to do the sine. Now here's my function I'm talking about. That's the function I'm concerned with. What's the sine of that? Okay, So whatever you call it, just a generic, sine of f maybe. Okay. Well, if you plug in a 1, what's 1? What's natural log of 1? Natural log of 1 is 0. So 1 minus 0 is positive. If you plug in a 3, what's natural log of 3? I bet it's going to be bigger than 1. Natural log of 3 is 1.09. So 1 minus 1.09 is negative. So what does this tell me? This tells me that this argument right here, that statement, is only true between if x is between 0 and e. Why is this important? That's important because that's the argument of this logarithm. I need that argument to also be bigger than 0, positive. What does this tell me? That tells me the domain of my original function is 0 to e. Is this domain right here. That's the domain of my original function that I'm at h here, because that 0 to e will ensure that that my overall function h, the logarithm, has a positive argument, which is a mandatory thing. Okay, so all of that to explain that the domain of h, the domain of my original function h, is 0 to e. Okay, that's a good little review of algebra there that I hadn't really anticipated. The domain is 0 to e. Okay, now let's go back to the critical value discussion. Okay, we already said that 0 is not the domain. 0 can't be a critical value. We said there are no solutions to the derivative set equal to 0 because there's a contradiction here. So there are no critical values. Okay, well, okay, you might say to yourself, well, if I plug in an e on the denominator, natural log of e is 1. You get 1 minus 1, 0. But notice e is not in the domain of the function. That's an open interval. So e is not contained. So there are no critical values. No critical values. I think this is the first time we've seen this. No critical values. Okay, and now the question is, well, okay, well, what the heck do you do if there's no critical values? Well, first of all, observe that, remember Fermat's theorem in whatever section 1 or 2 a long time ago in this chapter. Fermat's theorem said that if you have a local extrema, it has to occur at a critical value, which means if you don't have any critical values, you don't have any local extrema. Okay, another way to think about it is, to have a local extrema, you have to change from increasing to decreasing, or vice versa. Well, if there's no critical value, there can be no change from increasing to decreasing. Furthermore, I guess the final conclusion is that if there's no critical values, that means the function is either always increasing or always decreasing. And so I guess our two main observations are no critical values, well, I guess maybe 3, no critical values, which means no local extrema. And furthermore, the function is either going to be always increasing or always decreasing. To figure it out, just make a chart, like a mini chart. What's the interval going to be? The interval will be the entire domain of the function. So there's no critical value, so we're not going to divide up the domain. We're just going to use the entire domain, 0 to e. And we're going to pick a test point. And okay, 0, remember e is about 2.7. So what's a number, a nice number between 0 and 2.7? Well, 1 or 2. Let's just do 1. And then we're going to do the sine of h prime, the derivative. So where's the derivative? There, it's boxed off there at the top. So what happens if you plug in a 1? Well, the top is negative, clearly, it's a constant. If you plug in a 1, you get x is 1, and then you have times 1 minus natural log x. Well, natural log x is 0. So you get 1 on the bottom, you get 1 times 1. So you get negative 1 over 1. In other words, negative. So the sign is negative. So what's the result? Well, if the sign is negative, the function is decreasing. So I guess the last conclusion here, and this is kind of interesting, is that h is decreasing over its entire domain, which is 0, t. No critical values, no relative extrema. It's decreasing. That is, it's always falling from left to right. All right, let's look at the graph real fast on these. Let's see. Back to the. Let's look at this interesting one first. So the one we're just talking about, h, natural log of 1 minus natural log of x. Quite the interesting function. Desmos is kind of weird at rendering it. But basically, yeah, it's having trouble. But basically, it does. Basically, there's an asymptote at the origin, and there's an asymptote. Look here. At where? What might this be? X equals e. The right hand side of our domain is an asymptote. Okay, and notice it is decreasing over its entire domain. And there's no little peaks or no little valleys. It's decreasing everywhere. For there to be a relative extrema, there has to be a change from increasing to decreasing or vice versa. There is no change. We're decreasing everywhere. So there is no extrema here at all. No absolute extrema. We're not really talking about absolute extrema, but there's no relative extrema either. No extrema. Okay. What was the middle function? The middle function was g, which was what here? Let's see. See if our solutions were right. 1/2 x to the 2/3 power minus x to the 1/3 power. Okay, that's an interesting function. So we said, what were our solutions? We said that there was a local max, or there's no local max. There was a local min at 1, negative 1/2. And let's see if that matches. Oh, that's not true. All right, look what's going on. Yeah, so notice 0 was a critical value, but the function was increasing from 1 to infinity. So yeah, 1 to infinity we're increasing. It was decreasing from negative infinity to 0, and then from 0 to 1. So negative infinity to 0, union 0 to 1. Now, why is it not decreasing at the origin? Because there's a vertical tangent line there. So there is no derivative at the origin, because for that brief moment, the graph turns vertical and there is no slope. It's undefined slope. So yeah, no relative extrema. No relative maximum. The only relative extrema is this local minimum, and there is no local max, which is exactly what we found. Okay, and then the last one was our trig function. Let's go back up here and see what it was. 1/2 something or another. So it was 1/2 x minus cosine x, I believe. And I believe it was 0 less than equal to x less than equal to 2 pi was our restricted domain. Oh, come on. Are you not wanting to cooperate? There we go. Okay. Yes, 1/2 x, plus cosine x. Plus cosine x. Okay. So what do we say? So there is our function over the restricted domain. We said there was a local max at pi over 6. Yep. Pi over 6 is the location of a local max. Yep. A local min at 5 pi over 6. Yeah. And let's see if those y values are correct. So the exact y value of the local max is, let's see, pi plus 6 square roots of 3 divided by 12. Is that about 1.128? Yep. 1.128, so that's the correct y value. Now, what about at 5 pi over 6, the y value of the local minimum was 5 pi minus 6 square roots of 3 divided by 12, which is what, about 0.443? Yeah, 4429 and change. So yeah, those, when you are reporting these for like a test or homework or a quiz or something, you always want to use the exact y value. I'll give you most credit if you approximate, but solutions should always be assumed that you need exact solutions. Never give an approximate solution unless you're specifically requested to do so. So this is the exact solution, the exact y value. The approximate y values were, I forgot what it was, 1.128 and 0.443 approximately, rounded to 3 pieces. Okay, so we had 3 interesting examples there. Again, I know these are a lot of work. They're only going to get longer from here to the rest of the chapter. This chapter gets problems that are very involved. So I try to stick to only a couple, 3, 2, 3 at a time to keep the lectures, in the 30, 45-minute range, which I think I am at, yes, 45 minutes right now, 46 minutes. So I'm going to go ahead and wrap it up, but I'll catch you in the next videos. Again, always feel free to reach out if you need help. I'm here to help online, or you can always stop at my office. All right, talk to you soon. Bye.